Okay, everybody. So now we're going to continue into section 7.3. And we've learned some fascinating things about differential equations. We've learned some fascinating things. In section 7.3, you're going to actually see some differential equations that have explicit solutions. In other words, you can solve the differential equation. And separable differential equations, we can use those differential equations. We can find a solution. Usually can find an explicit solution. So let me let you copy this example down. Okay, so here is an initial value problem that we wish to solve. And the initial value problem is y prime equals x squared over y squared. And we're given an initial condition that when x is 0, y equals 2. Okay, so of course, this y prime is the same as dy dx, okay, in Leibniz notation. And that's going to be very helpful. So let's go ahead and look at how we would solve this. All right. So we're going to do a procedure called separating the variables. You'll notice that in this problem, the variables are x and y. X is the independent variable and y is the dependent variable. So what I'm going to do is I'm going to write y prime right away as dy dx. And what I want to do is we want to get the y variable functions and information on one side of the equation and the x variable information on the other side. So what I can certainly multiply both sides of the differential equation by y squared. Okay, and if I do that, I'm going to get y squared times dy dx equals x squared. But now we recognize that dy dx is the ratio. I mean, it's a derivative, it's a slope, and it's a ratio of two differentials, right? a dy and a dx. How many remember studying differentials in Calculus 1? How many remember that? Okay, Justice remembers, Michael, and so okay. Well, look, why don't we multiply both sides of this this equation by dx. I'll multiply by the differential dx, because when we do that, on the left side, you get simplification. And so now on the left side, you have y squared dy equals x squared dx. And you've separated the variables. The variables are separated. Variables are separated. Well, I'll get there, not now. I'm not there yet. But we will get there. So now, what do we want to do? We want to find out, you know, the goal here is to get a solution for y. You know, what is y equal to? What is y equal to? Well, this differential equation, this is a differential equation. It's just in a different form from what we started, but it is a differential equation. If I were to integrate the left side, what would I have to do to the right side? If I were to integrate the left side of the differential equation, what would we have to do to the right side? We'd have to integrate as well. That's right, Rodrigo. And so this is how I'm going to solve my differential equation, because the antiderivative of y squared is y cubed over 3 plus a constant of integration, which I call C1. And then on the right side, the antiderivative of x squared with respect to x is x cubed over 3 plus another constant of integration. And you notice I don't name the constants the same. I call the constant on the left C1 and the constant on the right C2 because they're allowed to be different. So we should have C1 and C2. And that's important for when you show your work, you know, on your next exam doing these kind of questions, that you remember to do that. Are there any questions up to here? Are we good so far? Well, am I able to solve for y? Can I solve for y? Tina's good. Thank you, Tina. Can I solve this? Can I get the y by itself in this equation? Yes, we can. So I'll move to the next page. So, well, what I'm going to do first of all, is I'm going to subtract a C1 on the left side and on the right side. And this will get to Nell's question. I'm going to subtract a C1 on the left side of the equation and a C1 on the right side of the equation. I'm going to subtract those constants. And what's going to happen is you're going to get cancellation here. And on the right side, you're going to get x cubed over 3 plus c2 minus c1. But what I'm going to do is I'm going to say let c3 equal c2 minus c1. I have to carry these constants around, okay? And I have to keep track of them, you know. So I'm going to let c3 equal c2 minus c1. And when we do that, we're going to get y cubed over 3 equals x cubed over 3 plus c3. But again, my goal is to get the y by itself. I want an explicit solution for y. And so what I'll do is I will, let me see here, one moment. I'll multiply both sides of this equation by 3. So I get a y cubed on the left side. And so y cubed then will equal x cubed plus 3 times c3. And I'm almost ready now to solve for y, so I'm going to let 3 times c3, I'm going to call it my big K. I'm going to call it big K. Okay, I could also call it big C. Okay, WebAssign tends to like the C, capital C, for its constant of integration. Not always, but. So now I have y cubed equals x cubed plus k, and I will solve for that constant k. I will solve for it using the initial value. But right now, I can say, look, let me take the cube root of both sides of this equation, and y will equal the cube root of x plus k. And that's a family of solutions. That's a family of solutions because k is allowed to vary. And actually, there's no restriction on k because you can have the cube root of a negative number as well as a positive number. So k could be any value. But again, we're interested not in a general solution to the differential equation. We're trying to solve an initial value problem. So if you think about the direction field for the differential equation, only one solution is going to pass through the point 0.02. But to find that solution, we have to solve for k. And so what we do is we say, all right, well, y of 0, we're given that equals 2. That's a restriction on our solution. So that means then we can uniquely find the solution for this differential equation. 2 is equal to y, x is equal to 0. 2 will equal the cube root of 0 cubed plus k, so 2 is the cube root of k, hence k is 8.
How did we get 8?
Well, the cube root of what number? Cube root of what number would equal 2? Now, okay, but okay.
Oh, okay, I get it.
You could do this though, Tyreek. You could take the cube root so like here, we could put in another step. We could say, I want to solve for k. So I'll take the cube root of k and raise it to the third power. That's going to get me 2 cubed, so k will equal 8. All right, is that all right?
Yes, thank you.
All right. Are there any other good questions? All right, well then let's, if we're good, we'll move to the next page. So now, the solution to the initial value problem is y equals the cube root of x cubed plus 8. And I'm not expecting you to copy this table down. This is actually an example from the book. If you go to section 7.3 and look at the first example, that's what we did here. But I thought it was good to just have a picture. So figure 1 here, figure 1, shows graphs of the family of several members of the solution to the differential equation. The solution to the initial value problem is shown in red, and actually I'll have to highlight that in red. We see here. So y of 0 equals 2. So that's going to be, there's 0, 2 right there. So here's the solution. Passes through 0, 2, that coordinate there. And you know that's, I mean, based on the picture, you know, this is 1, 1. So, you know, that's 2 there. So, I mean, maybe on the web assigned homework, had to be a little careful. Remember the matching problems where you had to pick out the solution, the right solution? Sometimes I think those aren't too hard, but you know, I don't know if anybody missed any of them. You wouldn't be the first. You can be honest and let me know if. All right. Are there any questions on this problem before we move to the next one? I want to do one more. I want to do an application. So I mean, basically, the separation of variable problems, you have to try to separate the variables. Sometimes it takes a little thought on how to do it, but that's what you have to do. And all right, Tina got them right, but well, I hope you weren't just lucky. I hope you knew, you know, how to do it there, Tina. I hope you did. I assume you did, but. All right, we're good. I'll move to the next problem. All right, time for a word problem. Time for a word problem. All right, so take a moment to copy this word problem down. We're going to do a tank problem. Okay. All right, so take a moment to copy this example down. Okay, so let's take a look at this problem. We have a tank that contains 20 kilograms of salt dissolved in 5,000 liters of water, and brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. Okay. The solution is kept thoroughly mixed and drains from the tank at the same rate. Okay, so how much salt remains in the tank after half an hour? So just a few sort of common sense questions. So there's a brine, a salty solution that enters the tank at 25 liters per minute. The solution, the briny solution gets mixed into the tank, and the tank is drained at the same rate, 25 liters per minute. So why is the tank being drained out at the same rate that the brine solution is getting entering in? Why are they doing that? Why do they need to do that? Or, why are they doing that? What if, for instance, what if the solution drained from the tanks more slowly than the rate at which the briny solution enters the tank? Brine solution enters the tank at 25 liters per minute. What if the tank only drained at 10 liters per minute? That's right, Felicity. Very good. It would overflow. It would overflow. And that's right, Tina, limited volume. So it makes sense. This makes sense that you would drain the tank at the same rate. But they're asking how much salt remains in the tank. How much salt remains in the tank after half an hour? So what's one thing that we have not been given in this problem? We've been given in chapter 7 differential equations. All the previous problems, we were given, for each problem, we were given a what? We were given a we were given a derivative. We were given a, that's right, Michael, we were given a differential equation. Here we have to get the differential equation based on the context of the problem. So here's how we do it. Let me go to the next page. First of all, I'm going to define y as the amount in salt kilograms after t minutes. Now we know that the salt content in this tank is going to change because we're pumping in this briny solution, we're mixing it, and then we're draining at the same time. The solution draining it out of the tank. So the solution in the tank is always the same amount of solution, but the solution changes its nature based on this process. So the salt content is going to change. It's going to be a function of time. But what I want to do, remember, I'm looking to find what y of t is. I want to find out what y of t is. So in order to how much salt remains in the tank after half an hour, that means half an hour is 30 minutes. So ultimately what I'm looking for is the amount of salt in the tank after 30 minutes. And I should say amount of salt, I should probably add the words in the tank, right? I should add the words in the tank. Let me just add that. So what we have to do is we have to recognize that then, well, now what I want to do is write a differential equation. dy dt. Since I'm looking for y, my differential equation is going to be dy dt. So dy dt is the rate at which salt is in the tank with respect to time. And we have to recognize that this derivative is dependent on the rate at which salt is coming into the tank through the briny solution, and then the rate at which the salt is exiting the tank as we mix the solution and drain the solution. So the units for dy dt, and this is very important, the units for dy dt are going to be in kilograms per minute. Kilograms per minute, because salt content y is in kilograms and time is in minutes. And this is helpful to make sure that I know I'm going to get the right differential equation. So we have to identify rate in, we have to identify rate out. Well, what's the rate in? What's the rate in? Okay, so the briny solution is entering the tank at, that's right, Tina, entering the tank at 25 liters per minute. But that's not the rate I want, because my units have to be in kilograms per minute. So, I mean, I'm trying to find the rate at which the salt's entering the tank. So I'm going to take 25 liters per minute and multiply it by the concentration of the briny solution, which is 0.03 kilograms of salt per liter. Okay, 0.03 kilograms of salt per liter. And so now when I do that, notice that the liters simplify, and I'm going to have 0.75 kilograms per minute. That's going to be the rate at which the salt is entering the tank. Okay, how many find it helpful to write in the units here and here see the rate in, the units for rate in would have to be kilograms per minute, and it is. Okay, how many find that helpful to put the units in? Yeah, I agree, Rodrigo. I sure do. Does anybody else? Hopefully. Okay, thank you, Michael. Thank you, Eric. Excellent. All right, well, now we have to determine the rate out. Now we have to determine the rate at which the salt is exiting the tank. But the rate at which the salt's exiting the tank, well, we know that we're draining the tank. We're draining the tank at the same rate that the brine solution comes in. So the rate out, it's going out at 25 liters per minute. Okay, the mixture. But then the concentration is going to be YT kilograms over 5,000 liters. Okay, so concentration, in the tank, we don't know. I mean, we know that since Y, remember how we defined Y? Y was the amount of salt in the tank after T minutes. So the concentration of salt in the tank would be the amount of kilograms divided by how big the tank is. And the tank is 5,000 liters of water. Okay, and the rate out is a variable rate. Okay, the rate of salt coming in the tank is constant, 0.75 kilograms per minute. But since the rate of water leaving the tank is going to be dependent on the amount of salt in the tank at time t. So you get Y kilograms over 200 minutes. Let me see. Not Now had a question. How come we couldn't use 20 kilograms for the rate out? Well, the thing is, you see, the I want to say this the right way. Initially, the salt contains 20 grams. Initially, the tank contains 20 Initially, the tank contains 20 kilograms of salt dissolved in 5,000 liters of water. But the salt content's not going to stay that way because you're pumping this briny solution in. Okay, so the 20 kilograms of salt is just an initial condition. That's initially how much salt is in the tank, but it doesn't relate to the rate out. Very good question, not now. And Tyreek, you had a question?
Yeah, I was asking the same thing.
Okay. Okay. All right. Well, now what we want to do is we want to substitute in our 0.75 for rate in, and we want to substitute the y over 200 for the rate out. And then we'll have a differential equation that we can work with. So I'll move to the next page if that's okay. All right. So now that's what I do. Right here, dy dt is 0.75 minus y over 200. But I'd like to get a fraction on the right side. So, 0.75 is like 0.75 over 1. So the least common denominator is going to be 200 here. It's going to be 200. And so if I convert the 0.75 to a fraction where the denominator is 200, I'm going to get 150 over 200. And so that means dy dt is going to equal 150 minus y over 200. That's your differential equation. So in section 7.3, for some of the problems, for the applied problems, you have to come up with the differential equation, just like we're doing here. Are there any questions up to this step? All right, well, the next thing we want to do now is try to solve the differential equation. We want to try to solve it, right? So dy dt is equal to 150 minus y over 200, and I'm going to separate the variables. So at this stage here, okay, I'm going to multiply by 1 over 150 minus y. I'm going to multiply both sides of the differential equation by 1 over 150 minus y. And we'll note here that y would never equal 150. Okay, and there's a reason for that. We can, practically speaking, we'll talk about that at the end. But then what I'm going to get is this differential equation: 1 over 150 minus y dy equals 1 over 200 dt. What can we do to both sides of the differential equation? What can we do to both sides now that we've separated the variables? We want to solve for y. So what should we do to both sides? That's right. That's right. That's right, Rodrigo Kahindi. We want to integrate. That's what we're going to do. And thank goodness you learned a lot of integration techniques so that you can handle these kind of problems. All right, so on the left side, the right side, that's no problem to integrate the right side. What technique are we going to use to integrate the left side? So let's see, you've had substitution, integration by parts, so use substitution. That's what we're going to do. So let's go to the next page. Okay, we want to try to finish this problem up, although we don't want to rush, but all right, so I'm going to let, on the left side, I'm going to let u equal 150 minus y. So du equals negative dy. So negative du equals dy. And so on the left side, I'm going to have the integral of 1 over u, negative du. And then on the right side, I'll factor out the 1 over 200. All right, so we integrate the left side. The antiderivative of 1 over u is the log of the absolute value of u. We integrate the right-hand side. So we get the log of the absolute value of u equals, well, what we get is, at this stage, we get negative log of absolute value of u equals t over 200 plus c over 1. You notice the first constant. Now, I want to make a comment here. So, of course, technically speaking, we get a constant on the left side. We get a constant on the left side, and we get a constant on the right side. But we know that to solve for the variable u, we would subtract the C1 constant from both sides. So we would end up with a constant just on the right side. So it's okay when you do your work for these problems. It's okay just to have a constant added on the right side. It's okay. And on the left side, I have a negative log u, but I really want a positive log u, so I'm going to multiply through by negative 1. But on the right side, then, I get negative t over 200 minus c1, because I'm multiplying through the equation by negative 1. But minus c1, then, I'm going to call that c2. I could leave it as negative c1, but generally I like to, just. Now, to solve for the log of the absolute value of u, we're going to exponentiate both sides of the equation. But on the right side, e to the negative t over 200, e to the power negative t over 200 plus c2 is the same as e to the negative t over 200 times e to the c over 2 power. And what I'll do is I call e to the c over 2 power. I'll rename that constant as c3. You have to change the name of the constant. You can't use the same name. And I look for those kind of things in your work when you do your work on exams and so forth. Are there any questions up to this stage?
Yeah, how did we get the t over 200?
The integral right here the integral of 1 dt is equal to t. The integral of 1 dt is just equal to t plus a constant. That's antiderivative of 1. And so what I did, Tyreek, is then t is over 200. Does that clarify for? Does that are you comfortable with
Yeah,
that?
yeah.
All right, good. Are there any other good questions? All right, all right. Now, what do you think I should do with this variable u? What might I want to do at this stage? Am I interested really in solving for the variable u? Is that the variable I'm interested in? I'm really interested in solving for the variable what? The variable y. So what should I do at this stage with u? What might I want to do? That's right, Tina. Put 150 minus y back in for u, and that's what I'll do. That's what we'll do. So the absolute value of u becomes the absolute value of 150 minus y. So the absolute value of 150 minus y is equal to C3 times e to the negative 2 over 100 power. But it turns out that 150 minus y is always going to be positive in this problem. In other words, y, the amount of salt in the tank, it'll actually approach 150. But it's, hold on, I got an error here, hold on. But as time goes on, the amount of salt in the tank will approach 150. But it'll never quite reach it, you know, it'll get close. But y is always going to be less than 150 kilograms of salt. And so therefore, 150 minus y is always positive. We can drop the absolute value. And incidentally, this here, the plus or minus part, I have it there, but we don't really need it. We don't really need it by virtue of the fact that, you know, y is 150 minus y is positive. So what I'm going to do now that I'm done playing around with the constants, I'm going to call C3 equal to C. So now I solve for y, and y will equal 150 minus this constant of integration. Well, just this constant. Y will equal 150 minus C over, sorry, y will equal 150 minus that constant times e to the negative 2 over, I'm not saying this right, I'll do it one more time. Y will equal 150 minus that constant C times e raised to the power negative t over 200. Okay, and you notice I'm not using decimals here. WebAssign likes exact answers. So you want to do these problems being exact. Okay, we can use a fraction here, right? Now the thing is, we need to figure out the constant c. We need to figure out the constant c. What is the constant c? Well, c, we need an initial condition. We were given in the problem initially that there were 20 kilograms of salt in the tank. So to solve for that constant, I'm gonna apply that initial condition to the equation. Y of 0 equals 20. That equals 150 minus C times e to the power negative 0 over 200. And e to the negative 0 over 200 is just e to the negative 0, right? But e to the 0 is 1. So it turns out that C will equal 130. And so now you have you have found what y equals. Y, the amount of salt in the tank at time t, will equal 150 minus 130 times e to the power negative t over 200. Absolutely fascinating that we can, do these kind of problems. Are there any questions so far? All right. Well, now we're able to figure out after 30 minutes how much salt is in the tank. Okay. So I'll move to the next page if we're okay. All right, well, let's go forward then. So after 30 minutes, the amount of salt is, and I should say the amount of salt in the tank, right? So after 30 minutes, the amount of salt in the tank, well, we're just going to substitute in 30 for t. And we're going to get 38.1 kilograms. So WebAssign usually gives instructions about rounding. And of course, you have to always look at the WebAssign instructions carefully, right? I think you're learning that from the exams, right? To look at the instructions carefully and all right, so we've solved the problem, but we can make a few interesting comments here. Notice that as t goes to infinity, what would the eventual amount of salt be in the tank over time? Well, if we take the limit of y of t as t goes to infinity, okay, what would happen to e to the negative t over 200? As t goes to infinity, that acts, that like goes to like e to the negative infinity, right? That's what that goes to. And that's like 1 over e to the positive infinity, and that's 0. So what's happening, I think it's pretty clear this is an e, right? It has to be an e there. So this goes to 0, that term, and you're left with 150 kilograms. And it makes sense, when we get these answers, so that term goes to 0. And incidentally, this problem is worked out in, well, I've added some detail to it, but it's worked out in the textbook as example 6. And in that example, they have a figure that shows figure 10 in section 7.3, example 6. It shows you just a picture of it shows the graph of this function y of t. It shows the graph of the function y of t and how the salt content approaches 150. But it makes practical sense because over time, the concentration in the tank is going to approach 0.03 kilograms per liter. So it doesn't matter how much salt you start with in the tank. If you're pumping briny solution into the tank and doing it like forever, over time the solution in the tank is going to resemble the briny solution. It doesn't matter how much salt was in the tank originally. Over time, it's the tank, the solution in the tank will resemble that briny solution. And so if you think about it then, the concentration of the briny solution is 0.03 kilograms per liter, and you multiply that by the 5,000 liters, that's the size of the tank, you're going to get 150 kilograms. Okay, so I think it's very, how many think that's actually pretty cool, the connection? I mean, of course I love it, but how many of you think, hey, this is kind of a cool problem, a cool engineering problem, or a cool chemistry problem? How many? I mean, I know you want to see it on your next exam, right? This kind of problem, right? Or all right. But Kahindi, you think it's cool, right? More or less. So I got it. Hopefully, I'll get a few thumbs ups. Few thumb ups. No comment. Okay. All right. All right. So people are a little reserved about it. Okay. Well, let me. Are there any other questions before we only have a little bit of time here? I want to get. Let me stop the recording.